Welcome to a discussion with Jikun Kang regarding Think Before You Act, Decision Transformers with Working Memory. In this discussion, we're going to take a deep dive into transformer-based decision-making agents and see how different memory approaches to those can benefit or hinder performance. The first question I would have has to do with the forgetting phenomenon that you mentioned in the introduction of your paper. It seems like, just on the first reading of this, that the motivation for producing your paper is kind of to get around that phenomenon in particular. Would you say that's the case, or would you say the motivation for this paper is somehow different?
From my perspective, I think the motivation is something quite different. So before we jump in this project, we're actually thinking about building a foundation model for reinforcement learning. Because at that time, we were kind of emerged in the world, everybody is talking about foundation models, especially in the NLP, language models. And we want to build this model that can play a lot of kind of games, for example, Atari games or other kind of games. And at that time, we were thinking about, okay, if we want to jump in this, maybe we need a large model to learn everything into the parameters. That's how it goes. You train your models, and hopefully every neurons or every parameters remember the actions, remember the trajectories you have in your past experience. So we have a question, because I'm a typical RL guy. I have a question, maybe for some games, some of the trajectories learned before could be useful for the future. And that comes to this kind of idea that maybe we can explicitly remember things that we want. So it's not really about the forgetting things, but about remembering things. That's why we want to use this memory. But I think that's not, these two things are not very conflicted with each other. It's kind of related. So yeah.
So if we talk about the philosophy of a memory like that, how does that differ from the implicit memory that you have in a large language model already, or some kind of transformer-based model? You have a big set of parameters, and arguably you have the equivalent of a memory, even though it might not be considered a dedicated memory within that model itself. How does the approach you're trying to take here differ from that on the fundamental aspect?
Sorry, if you were talking about whether current transformers have this kind of issues, or you want to think if we can yeah, please.
I'm talking about a network application, like a generic neural network application, let's say, to a problem. You would have, and we're seeing this in the large language models that are coming around now, a bloating in the size of those. So the networks themselves are becoming increasingly large, and to some extent, you could make the case that that's a way of introducing more memory into the system. You're making a larger network to be able to capture the desired behavior in more situations. And it seems like the working memory approach that you're taking in this paper that we're going to get into in more detail takes a different kind of approach to memory in general. And what I would like you to do is highlight the main differences, the fundamental differences between the approach you're taking and the approach that's being taken in networks that don't have a dedicated memory component, let's say.
Sure. Yeah. So think about our current transformer models. We don't have a dedicated memories for that. We just hopefully everything remembered in our networks, in our parameters. So next time when we use it, hopefully we can trigger those neurons that has been remembered the things you want and use that information to make your decisions, or generating things for you. But that's not always the case, right? Because you're not explicitly trigger those things. You're not explicitly using those informations very efficiently to help you make decisions. That's why we want to have a fundamental module, have a way of explicitly, we can trigger these things by our hands, or we can trigger these things by using the input or using the things we want. So I think that's a fundamental difference, how you trigger the memories. If you want it passively, I think that's how the transformer module is working right now. If you want it actively, you want to actively use the information, especially some informations may not be conflicted with each other, and you want to merge all those memories into the one thing. So I was thinking about that how you compress your memories, how you compress your information. Because if you remember everything into the transformers, you just remember things. You cannot compress the information. For example, you just learn into the parameters. And if you trigger several different neurons, maybe Maybe they get conflict to each other. Maybe they just talk to each other. That hopefully. But if you compress information, you can somehow like control the way you learn this information. You can control the way they combine to each other. So this information may be more compressed, more information, higher entropy. That's good for your future decisions making.
You mentioned quite early in the paper a comparison with the kind of working memory that you're adopting here in this paper compared to something like where you have a separate memory and you would, for example, use k-nearest neighbor search to find sort of the relevant information or something like that. Could you elaborate on a little bit more specifically on what the memory approach you're taking is and how that would contrast to the example that you mentioned in the paper with a more external, if I understood it correctly, type of memory?
Yeah, that's totally correct. So what I have in mind is from the cognitive science, we have a working memory. The working memory is something small, compressed, which is useful for you for your making your decisions. When you're thinking about things, you want to make your thinking slow. You want to like go through some kind of modules, use your past experience, and use this information for your future decisions. Let's take an example as a dynamic programming. When you do a dynamic programming, for example, have a lookup table. You have a lookup table, you remember the intermediate results when you do the dynamic programming. But after this, you just when you're writing a new results, you maybe want to use this lookup table, check the older results, and use that older results for the future. But this doesn't have to be really large. You don't have to be something like a vector database we have right now, like the RAG or all kinds of or the website kinds of things. Because what I have in mind is I want to make this fast because I want to put this memory inside of the transformer. Inside of the transformer, it has to be quick. It doesn't. I don't want it to be lagabits. I don't want it to be the bottleneck of the output, the computation cost. I don't want it to be the time cost. And on the contrary, the external memories, like what I said, the vector base or the website, you want to search information you want. That takes a long time, right? That needs some specific search method, or like the things I mentioned here. Maybe you want k-nearest neighbors, or you want other kind of things to like find the information you want. So I want to make these two things totally different. I would say like which one is better. I just want to use the working memories when I'm making decisions. I want to use the information I learned before. I want to make it fast.
If we consider the split between different quote-unquote memories in the system that you're building now, you have this working memory that you're describing. My understanding is that you have a transformer-based model that you're using in combination with this memory, and that the transformer-based model somehow contains the majority of information, and that working memory, as you alluded to in your explanation now, is a smaller kind of memory that is quickly accessible and able to respond to new scenarios quickly. I don't want to get into too much technical detail, but I just want to get an appreciation for how does the delegation of memory work? You have like some smaller subset, it seems, in this working memory, and then the rest in the larger, like just encoded implicitly in the transformer model. How do you go about making a distinction between the two?
Yeah, the things, as you mentioned, the first thing is size. Internal memory, the working memory, small. External memory can be huge, can be largely. This is one. The second is whether you put this memory. Yes, you can add this as an outside module, like totally outside of a transformer. Have your transformer have this memory module, talk to each other. Doesn't matter. This is like the kind of things you add upon, or you put this memory module inside the transformer, especially inside of some part of the transformer. Make them talk more quickly, and make the things doing faster before you output something from the transformer. I have more detailed, motivation or things that I have in mind. So if you think about this as like our own laptop or personal computer, we can have this memory like cache, something that you read is really quick. You use this information, only a piece of them make you help you run your systems, and this is working memory. And the external memory is like your disk, remembers a lot of things, a lot of different kinds of things. So essentially, if you can load your information from your disk to your cache, that would be the great case. But in here, I'm only talking about, adding this cache, adding the working memory into the transformer module makes a huge difference.
Okay. Is that what we'll get to this in more detail in a second, but is that what the lower rank adaptation is tasked to do? Is the core objective of that to take information from your larger implicit memory and then transfer that into like the cache or the working memory?
That's not the part to talk about in this paper, but LoRa is kind of like how we fine tune the memory. So we want to use an efficient way, a small way, like light way to tweak the memories, making it useful for the future, for the on-scene scenarios, especially.
Okay. So then maybe let's get back to that once we discuss the architecture in particular, because I think the figure will be helpful. Just before going there, I want to have a look at just the first figure here as well to give some motivation now that we know kind of what the paper is about, what the idea for applications is. So you have this figure. Could you please just introduce what the idea with having this kind of working memory would be in the context of an application?
Sure. So let's think about a case we're playing games. We're playing Atari games, and this robot here is just our agents, it's ourselves, or our algorithms, transformer module specifically. So in this case, we're like trying to say that, okay, in these kind of games, especially Asteroids Deluxe or Space Invaders 2, there are some things, relations between this kind of things. For example, Space Invaders 2, both kind of share the same concept. You're shooting games, they share the same things, but maybe a little bit different. So what I want to do is, when I learn the things from one specific game, Space Invaders, I want this information to be useful for the future, learning for the Space Invaders 2, or I just play this Space Invaders out of the concept. So by doing this, I want there's a memory, especially I call it working memory. This memory is small, compact. I want to remember the things, remember the trajectories or the information I learned before, like the useful trajectory, the useful policies I learned when I play Space Invaders. And this kind of things maybe this because Space Invaders information maybe just stored in the specific working memory area, and that's the case for each of the games, hopefully. And also we have a shared place. The shared place can always triggers when you play this kind of games, because you are always playing Atari games. And these shared games just help you to make decisions, make some kind of like useful decisions, because you're playing a Joy-Cons, you're looking at the frames and using information for your future playing games.
Very good. So then let's dive into the meat of the discussion and look at the architecture itself that you developed. So I think this figure would be quite useful to have for reference when we go through the transformer model. So specifically, it's named Decision Transformer with Memory. Could you start just, without going into detail on the right-hand side of the figure, just talk about the information flow going through this architecture?
Yeah, sounds good. So typically, I think everybody is familiar with language models, and the decision transformer is kind of an application that you apply language models, applying your transformer modules into the reinforcement learning concept. So here, the input, instead of the sequence of your sequence of tokens of your languages, there's a sequence of tokens of your trajectories. The trajectories consist of 3 tuples specifically. It's defined by the Markov decision process. You have a return to go. There's an R hat. You have state S and your action A. And because it's a time theory things, you have a different this kind of tuples in terms of time space, and you use them at the trajectory and at the input to your encoder and positional encoding. And the encoder positional encoding is basically the same at the transformer module. And the next thing, you go to your attention module. At the left side, this pink area. And you have a bunch of different attention blocks here. You use your self-attention, look into your old trajectories, look in the information you have, and use that to make predictions for your next token. And output here, you have an MLP layer, which is called action decoder. It's decoding your high-dimensional vectors back to your real actions. because we're making decisions. In our RL concept, you care about the actions. So this is typical decision transformer architectures. But here, we want to introduce this memory inside of this attention block. So into every attention block, we want to have a way to control the information flow into the attention module and flow back to the next attention block. So this memory is actively shaping the information by interacting with attention modules. And this memory is like what I told, like something you used before and something that you have right now to be remembered. Yeah.
And this, just to clarify, is the working memory that we're discussing now. So this would be the very specific, smaller. Okay. Yeah.
Yes.
Good. Before we jump into this one, I would have a couple of follow-up questions on the general flow. So first of all, we take these inputs, this Markov chain of states, actions, and rewards, and we encode it. And based on what I could tell from the paper, we encode each of these. So in one of these tuples with 3 elements, we encode each element separately and then feed those in.
Yeah.
Is there a reason why we need to encode all of them? And is there a specific reason why we split those up and encode them separately as opposed to having one function for encoding like one of these observations?
Yeah, because rewards, the first reason is they are coming from different dimensions. So they have different dimensions. There are different meanings. So reward typically is a scalar. States can be the vector representations of your current frames, current descriptions of your first scenario, and actions maybe it's another kind of vectors that represents how you behave. So, because you want to make these three kind of things using your attention, self-attention mechanisms to talk to each other, to build the connections, make the relations. So the encoder here mainly works as like how we like project all those kind of things into the same space, especially in the same dimensions.
So it still seems to me like we could have defined a function that encodes all of these at the same time. The reason why I'm saying that is in splitting these up, you kind of, it seems to me like we're considering them to be independent. If you imagine one generic encoding function, you could so I'm not clear exactly what we're doing with the encoding here, but if we would consider the natural language setting, usually what you do is if you're encoding like a word, you would get sort of the semantic mapping with that, and you could cluster things based on if the semantic mapping is similar. And to me, it seems like we're kind of avoiding the some possibility of doing the same here by encoding these separately. So if we would have encoded them all together in one function, you could relate the action to the state and to the reward, and you could have the cross information between those three being taken into account while encoding the state too. It seems like we're giving up the possibility to do that for the benefits that come with separating these different parts of the observation. Is there a benefit of splitting them up like this that I'm missing? Because I see some utility in having them all together, like as one input to the encoder, and you could define the input of the encoder, I believe, so that you could put all of these into the input at the same time. But we seem to opt for the approach of separating them. Is there a benefit of that I'm missing in this context?
I don't think this. I think it's more like decision choice, design choice, and I'm not sure if I understand correctly. So, because if you have one function, the functions that is defined as have input dimensions, and you want to like have input dimensions equals to the combinations of all the three tuples, all these three factors.
So,
yeah, please.
Please go ahead.
Yeah, I mean, if that's the case, I only think this is a design choice.
Okay, maybe I'm missing something in the structure. So usually the reward would be a scalar, and then if you have the state, it's a bit more ambiguous perhaps what that's represented as, but let's say that that's represented as a vector right now. And this is also represented as a vector, and both of these have some fixed dimension. So let's say both of these have dimension n. Could you not make a 2n+1 length vector as a fixed input to your encoding function, and then always make it in the construction so that the reward is in the first place of that vector, and then that this is in sort of the place 2 until n plus 1, and then that the last part is for the action. So it seems to me you could define a function like that, and that you would get sort of the benefit of encoding all things at once, because implicitly your encoding function would take into account the relationship between these different parts of the observation. But there can be something I'm missing here. It was just an idea that I had reading the paper. So if it's a stupid idea, then
no, it's pretty interesting.
Yeah.
It's pretty interesting. Yeah. Now I understand your point. Yeah, we can actually do that. I don't say it's good or bad. I just think about if you want to, because we can think about the three kind of things coming from three different dimensions, three different space, and trying to mapping them into the same space. You actually, the way you can do that is, as what you said, you can concatenate those three things together and use the same encoding functions mapping to the same space, hopefully, and you just, whenever you want each tuple to just select from this this combined space, this combined representations, and select one of them. So that would make it. That would be if the input reward is dimension 1. The representation is still, if it's a projection, it's maybe still the 1. And then if your input dimension for the state is n, it's still the n. If your input dimension for the state for the action is m, it's still the m, right? Because you're doing the same encoding thing. And what I want to do is I want to make sure reward state actions both share the same dimensions. The reason why I want to do this is I want this three different I want the unique representations for all of these different tokens, and I want these tokens talk to each other. I want this because when they share the same dimensions, I can more easily do the matrix dot product, matrix multiplications kind of things. And I want the tokens especially talk to each other and make and use this talking information as part of things for your attention score, and use that to make the decision for the future. Does that make sense?
Okay. Yeah, I think I see a utility in it. So I guess once we get to we haven't really discussed this block yet, but once we're in this memory block or this attention block, where we're looking at the similarity between a new state that we want to act in, and we're trying to utilize this memory. We'll get to this in a second, but then we're using kind of a dot product between, I guess, the state that we're looking at and potential things that we stored in memory already. And is that a key point where we want the encoded dimensions of all of these to be the same, because then we can do easily a cross product between them? Because if that's the case, then I get the point, because then we simply want to compare it with a new state. We don't want to compare it with a full tuple of state reward action, because we don't know either the reward that we're going to get or the action that we're going to take.
Yes, exactly.
Okay.
And that's cool. And maybe not just states talk to the states. We will get to the details, but maybe states also talk to the actions, because it's a Markov decision process. You make the actions based on your states, or maybe it's also talk about the rewards, because it's kind of like the goal here. It's a goal, what you want to achieve.
Yes, I fully align with that. I probably explained myself a bit sloppy, but yes, I agree that you want the state that you're going to be observing to communicate with whatever you have in memory, regardless of whether it's a state or an action or a reward. Okay, very good. If we then move over to the details that we see on the right-hand side of the figure here, could you describe in a little bit more, more detail, how we actually retrieve this working memory, and how we can make use of that when we encounter a new state?
Sure. So I know this figure is not a good one. It's hard to understand at the first glance, but here's a small, I think the small intuitions or the way how it works. So when we have this memory, we can think of them as a matrix or a tensor. And when we have this input trajectories, this encoded space of these different tokens, and you want to use a dot product to check the similarities between your current input and your what you have in the memories. And the memories for the memories, for example, each row is kind of the same kind of information, share the same dimensions, for example, and it's remember one information. Each row remember one information in your memory. And when you're doing this dot product, you're trying to think about, okay, given the current scenarios I have, and the memories I have that I remembered, like what's the most similar cases I have. And by using this dot product, you select the positions you want to take into and use other kind of things. For example, I have the erasing vectors, acting vectors here. It's two different vectors that can learn and use them to control. Okay, given the scenarios I have, given the memories I remembered, what should I do? Should I just erase part of the memories I had before? Because that may be too old, not good for the current. Should I add something information I'm learning right now? Because this is attention blocks like built upon like stacked together. It's flow from one to another. So I want to say, okay, this information may be outdated. I want to update a bit. So these two kind of things just work out this part of rule. And that's part of the adding things, like you modify your memories. And the next part is, okay, have this, because I know this part of things, this part of locations, specific roles in these memories, I care most. That helps me most, maybe. And I just want to like use a learned way of extracting the information based on the similarities I have, because it's cross attention, and use those kind of things to extract part of the information, maybe not all of them, and part of the information from specific role, or part of the combined information from several different roles. Maybe one from the Space Invaders. If we take the Space Invaders as example, maybe when we play this Space Invaders 2, we take the information from Space Invaders and we take the information from the shared knowledge, because shared knowledge tells us how to play the Joy-Cons, and combine those two informations together to extract them back with your current inputs, and maybe just add them together and use that information for the next attention block inputs.
How does the model know whether to stick to information from a previous memory or whether to define a new action altogether? It might be, at least the way it seems to me, that you could have more available actions to you at the current moment than what your experience indicates. So if these are slightly different scenarios, maybe you don't have the equivalent set of available actions to you. So that's partly one scenario where you perhaps want to explore and not just use the memory. And then the other case would be if you just haven't done enough exploration, so you want to incur some of that. Is it like an epsilon greedy approach, or are you using something similar to decide between whether to pick something from memory or whether to simply go with a new action?
Yes, I have the thing to control. It's actually this beta here, beta in this figure here. It's called the writing strength. Like how much information you want to write to this memory. Because that kind of things is like, if, as what you said, if two things are quite similar to each other, because the current input is quite closely related to what you learned before, maybe you want to use more information from that. But if it's not too much, you want to like avoid using too much information from the past. You want to avoid that kind of things. That's how this parameters controls. It's like, it's more, or I think it's more like if we have a gating mechanisms in the neural networks that lets you control, okay, how much information you want to flow in or flow back.
Okay, so the writing strength of this beta parameter, it tells us how strong the working memory is allowed to write into the action of the current state. Is that the way to think about it? It's not the amount of influence the current state has on affecting the memory. It's the other way around.
Yeah, it's the other way around. And the way that you are talking about the importance, like the factors that you want to know how much information you want. That kind of things is defined by the cross attention. The cross attention, like have an attention score. Like you use like how strongly you want to use information.
Okay, and that's not related to beta. So beta is how strongly we persist a new state into the memory, or is it how strongly the memory is allowed to affect the action of a state?
It's into the memory.
Okay. And then we have the cross attention for getting effects the other way around, and that's the point where I'm curious how we decide whether to go for an action that we already observed, that we see as rather similar through the cross-attention mechanism, or whether we take a new action altogether. And to me, there are two ways that you could do that. You could have a cutoff criteria that says, okay, either you go completely with the action, or you take your own randomized action approach. Or as a second alternative, potentially you could let the state from memory that is the most similar have some effect on the encoded version of your state, and then through the decoding process, there's some like carryover of that effect, but maybe not entirely. Could you elaborate on how that works, which of the two approaches you take, or a third one if that's what you do?
Yeah, I think the way I'm doing here is actually totally automatically, and want to use this learned vectors to control how much information I want to know. So if two things, if this learned things is totally tells me it's zero, it totally tells me to not look into the memories, I can just go with like the normal transformer architectures. I just use my current information, use my current inputs, look at my states in the trajectories, and use that information for the future decision making. But if it's not, if the information is like closely related to what I have learned before, what I have right now in the memories, I'll use the informations and look into both of them. Like it's more like the compressed information. It's not exactly the states you have right now, but it's a combined information. Maybe you have the states if you have the time step t at your current trajectories s, and you have a similar time steps at your previous experiences, previous trajectories, and you combine those states together, mix them together, and use those information kind of like help you to do the decision. Or it's not, maybe it's not very related to states, but also related to actions you take.
Okay. Is there anything else about the architecture itself that you think is important to highlight before we move over to the evaluation and some results of this architecture?
I don't think there's too much. Maybe there's one intuitions I have for this architecture is, I think it's close. This is also related to the neural Turing machine that they back to, I think, 2014. That people want to use a way of making a memories into the Turing machine, help they remember things, especially intermediate results. That's kind of like working memories, and use those things to help you actually achieve complex tasks. So this is also related to that. The memory here plays as specifically working memories that you want to use the information you learned before, or you're learning right now, and use information for the future decision making. And one thing we want to highlight is the working memory here is not exactly the same as what we have in the cognitive science, because in that kind of things, in cognitive science, it's strictly the definition of working memory is when you finish your learning, you discard everything you learned. You discard everything you learned in your memories, because they think this is outdated. This is not necessary. Maybe like the lookup table you use for your dynamic programming. After you solve this dynamic programming, this lookup table is just outdated. You can just discard it for free. But here, we want to keep these memories. Maybe we'll talk about that later in the evaluations. But this memory will keep for the future decision making. Because we want to make sure this memory is useful, not only for your training, but also for your auto distribution, generalizations, and also adaptations to unseen scenarios.
Very good. So moving on to just the introductory part here of the evaluation, you list these 4 key questions that you wanted to answer for the model. Could you elaborate a little bit more on what the idea is behind these? So what is it exactly that you're interested in investigating?
Sure. So initially, when I design these evaluations, I want to see first, I want to see the generalizations, because I want to see, okay, the memory I learned actually helps for the scenarios I never experienced before. But scenarios could be the similar. So one of the assumptions that happens in this evaluation is all of the tasks, all of the games are coming from the same distributions, same task or same game distributions. So that's why when I do the evaluations, if I test on the Atari games, I only play Atari games. If I test on the other like robotics tasks, I only test on robotics tasks. And that's the case. So the first one is what I said. I want to check, okay, this memory is actually useful when I'm making decisions that I never think before. That's for the model generalizations. A second one is, okay, this memory, what if I add this memory and it's harm to the training? Maybe that's things I don't want to have. Because if I have the current transformer module can learn things pretty fast, can learn things pretty easy, why not just use the current model? Why we have to design something different and harm the training performance? Because training is always is all the hardcore things in the language models. And the third one is like, does this transformer model scales with the model size? Like when we increase the model size, increase the scales of your memory size, how does that help? I just want to know those scalings. And the fourth one is actually more like detailed way of thinking whether the memory module is helpful. Because generalizations typically tells you how it works in a general fashion, like maybe it works well in the okay-ish in your new scenarios, but that's not the perfect that you want. So you always, or you sometimes you want to fine-tune your model a bit to adapt to the new downstream tasks, the tasks you've never seen before. So I want to test this kind of things also. I want to know, okay, this memory, if I fine-tune this memory, it's not harmful for a better decision making, for more optimal solutions. So those are kind of the flows when I design these evaluations.
What exactly do we mean with question 3 with the scaling? So we're saying that the performance scales with the size, but in what sense are we talking about performance scaling with size?
Yeah, there are actually two specific criteria I'm thinking. The first one is we have a scaling loss for the large language models. When we increase the model size, we tend to have more space to learn things. We tend to have better generalizations. We tend to have better performance specifically. I want to test that. When we have this memory, increase the model size. How does it think? How does it work? Like does this memory still work for when we increase the model size? Because everybody, maybe not everybody, but some of them just wants model to be as much as we like. And second one is mentioned in the appendix. What if we scales the memory size? Do we have to do do we want to have a very small size of model memories that maybe is good enough for your decision making, for your working memories, or you want something larger, maybe not as large as your external memories, but something larger enough to remember as much possible information as you can. And maybe there's a relation between this model size and this memory size, like how the two things related.
Okay, very good. So let's focus on the first one then, the generalization aspect. And I think table 2 is the one that primarily looks at this. Would you mind explaining what we see in the table and also elaborating briefly on what the baseline models are that we're comparing to?
Sure. In this tables, we specifically take 4 held-off games, like the games never seen before, as a testing scenarios for this for the proposed decision transformer memory kind of things. And the comparison games we have here is, the first one is multi-game decision transformer. It's a successive work of original decision transformer applied to the multi-games, the different tasks, especially in Atari games. And this kind of comparisons shows, okay, the old fashion or the classic fashion of training the models into the parameters, how that work in the general out of distribution like out of tasks generalizations. A second one is called a recurrent memory decision transformer. It's It's more like thinking about adding a cell state. It's related to the LSTM, short-term memories. You have a cell states into the this multi-game decision transformers. So you can take that as a different approach to add this memory into your decision transformer. And the third one is ours. And there's a funny story that I just had. I met the authors of RMDT at the SML this year, and we had very nice discussions about like how memories should be approached. And they told me the previous version, the version I have right now, is their previous versions, and they have a new one, make things more how to say, it's more adapted to the new things, because they abandoned multi-game decision transformer, and you know what, they apply it to Mamba, apply their approach to Mamba, and they achieve good results, and I love that. It's really interesting to see how memories apply to different things.
Cool. If we look at the numbers in the table, we can see that DT mem outperforms the other ones quite significantly. What would you say is the main reason for that? Like, if we look at the baseline models, what is it that they're lacking fundamentally, which prevents them from achieving similar scores? Because they are also trained on not the same game, but at least the Atari suite of games, as far as I understood. How come they're performing, or they're underperforming significantly in this comparison?
Yes, that's why I think the memories helps. So first of all, the major difference between DTMEM and MDT is the memory part. We only add the memory into them, and I think that contributes most according to this figure. And the underlying interpretation or the understanding of this phenomenon is how you use your explicit memory for your decision making. Because for the normally generalization of your large language models or your transformer modules is to because you're trying to maximize your log likelihood based on your past experiences, and you're trying to use this log likelihood as a very vague or inexplicit way of triggering your past experiences. For example, maybe this alien is related to one of the games or one of the things you learned before. Maybe only related to the things that you remember as like how I should play this game. But that's totally depends on your next token predictions based on your attention scores and based on what you learned, the log likelihood, the log likelihood based on your training corpus, your training games. But decision transformer is kind of like on the opposite way. We want to explicitly remember the things. We want to know, okay, when this alien when we play these aliens and the games I played before, the useful information I learned before. Maybe it's a shooting game, maybe it's a chasing game, maybe it's something kind of games. If these things that I learned before, I can definitely use information I learned. I can definitely know when we're shooting games, we're shooting the target, we're shooting straight, we avoid enemies, these kind of things. And we use this information to know, okay, doing this kind of decisions, it should related to this kind of things I learned before. I should use those informations explicitly extract this kind of things, not based on the log likelihood, not based on other kind of things, but based on the similarities, based on the information similarities. And we want to use the information learned before to make this new decisions. And that's why I think that's memory helps. That's why there's huge gaps between whether you want to add the memories. Because as you can see here, the RMDT, that another one that adding this memory here, also performs better than the old one, than the MDT that doesn't have memories.
Okay, so the main difference seems to be that we're more specific in how we're trying to utilize the previous experience that we had with the new selection procedure. Okay.
Yeah.
Okay, let's have a look at training time as well. So I think that's the next table, this one. Would you mind elaborating on the training time that we have in this comparison and specifically why it's so much shorter in the DTMM case?
Yeah, this is an interesting phenomenon actually I found during the training. So first of all, I want to explain that DTMM 20 million is a size which includes 30 million of parameters, which is this transformer module, and 7 million size, including your learned parameters of your memories, operations, and the size of your memories. That's why it's 20 millions. So when I try to evaluate this, I want to see if adding a memories actually cause you learn slow. Let's make you learn slowly than before, or cause some other issues. But after I tried it, it's actually pretty interesting that that even though your initial states, your initial part is normally not as fast as your classic decision transformer MDT 30 millions here, but when you're training a long time, the memory tries to capture more useful information, and this useful information is even more like helpful for your current training, for your remembering or for your learning new things, new tasks, and that's why I think this helps a lot. This kind of things actually at the end it's decrease your training time.
I'm not quite sure I understood. So we have the memory, and the memory itself somehow helps us increase the time of training. Could you please go over that one more time? Like, how does the memory, the fact that we have a memory, actually help us speed up the training? Because to me, it seems like we're still having to go through the same amount of states as we would in the training, and we still have to like persist the same amount of information, even though the updates to parameters and things like that might be slower. But where's the fundamental difference in having a memory and not having one?
Sure. Maybe I should like start with this way. So this is more like the training is more like supervised training because this is offline reinforcement learning that you have datasets. The datasets is you have trajectories of what happened before, and you want to make predictions. The predictions is exactly the same that you have in your datasets. So you have a label for the actions you should take.
Okay.
So the training mainly just wants to mimic this information or mimic these trajectories you have in the datasets. When you see this previous states actions and you want to and the current states, you want to exactly predict the same actions according to your datasets. So supervised training. And when we use the MDT method, it's basically just learn like this way. It's trying to remember everything and use this to learn the underlying log likelihood of how you generate the next actions, and use that for your as objectives for your decision transformer. But decision transformer memory, our approach is slightly different because when you have a memory here, it actually helps you to make these predictions. That's what I think that helps because we learn everything in the end-to-end fashion. We learn the memories, the operations of the memories, and the training the training parameters of transformers at the same time. So initially, at the starting point, the memory is randomly initialized, the module is randomly initialized. The learning of the memory is not good enough. The transformer is not good enough. They're just trying to optimize the parameters itself to mimic what happens in your training task, in your training data sets. But with the parameters improves, your memories is gonna more and more organized. It's more and more structured, and the information is more and more stored, and the operations more and more learned. I mean the operations. I mean the way you operate your memories. And with that time going, this information goes fast. This learning things goes fast because you're not only just mimicking the things based on your current input of trajectories, but also based on your memories. And this memories help you to predict things that closely related to what you have in the data sets because you're training from. I think that's why it helps a bit.
Right. We have a few minutes left now, and not quite enough time to go through all the figures that you have in the results. I would ask from you if you wanted to summarize the key findings that you got from conducting the study. And if you want me to bring up a specific figure or a table in doing so, I'm happy to do that. But just like the main takeaways from the study, so that we get that in the interview as well.
Sure. In a short summary, I think I want to say in the high level way. We're emerging in the world that everybody talk about large language models, especially the success of different kinds of closed or open source models. Transformer modules is good, but the way of learning it is just implicit learning into the parameters. That's why we build our models as large as possible, because we want them to remember everything we have, everything we learned from this training data sets or training corpus. Memory is a different thing. As we can see this figure here, memory can help you first decrease your model size, because you remember things in a more efficient way, effective way, that you don't have to use the large models to remember everything. Instead, you use small parameters to help you learn how to operate with these memories, and you use another small memories to remember things. Maybe this is not a working memory, maybe this is a larger version of working memories, but memory is important. That's the first thing, help you decrease your model size. And second thing, the memory itself is actually good for your decision making, for your next token predictions, for your generations. I think that's in terms of how you leverage your past experience. You, as of like a human, when we want to interact with new things, when we want to learn new things, we always trigger something we learned before. When we meet you, maybe I think you as part of my old friends. I'm trying to learn your structures. I learn your patterns based on what I learned before, but it's not exactly the same because you have same information. I use information to tweak the memories I had before, so I have a better understanding of you. And that's a high level understanding of how memory works. That's the second thing. Memory help you to get a better performance. The performance here, especially what I want to say, is the first generalizations. That generalization is to unseen. Nicholas, I think first time today. I want to remember you fast and I use memories. And the second is fine tuning. When I fine tune my memories, I meet Nicholas more. I know Nicholas more. I fine tune more a bit. I know Nicholas as part of my important memories. So when I see a new person, maybe I use the features I learned from Nicholas to help me understand this new person. And that's what I want to say. I want to fine tune more about it. I want the performance to be better on the new thing scenarios. And I think that's all. That highlights all the information I want to convey in this paper. And I hope this can shed a light into the future research, make people more interested in how adding memories into the transformers, large language models, all those kind of things. Thank you.
Perfect. Thank you very much for wrapping it up so nicely, and thank you very much for a nice interview as well.
That's my pleasure. Thank you so much for having me here.